Hi, my name is Harlan. Welcome to the Machacon Mechanical Engineering channel. Today I will discuss about system head calculations using Hazen-Williams formula for head loss. And to illustrate the procedure better, I have chosen a specific project to discuss with you. A sewage treatment facility plans to build a lift station to pump sewage from a chamber to a higher elevation. The difference in elevation between the chamber bottom and the force main discharge point is 20 feet. A flow that would vary up to 900 US gallons per minute using a combination of identical pumps connected in parallel is desired. The force main is an existing 8-inch PVC pipeline having a total length of 4,000 feet. The force main consists of 15 units 45-degree elbows and one piece 90-degree elbow. A swing-type check valve, 2 pieces gate valves for the flow meter, 1 unit flow meter, and 2 pieces flexible connectors will be added to the system. All of these fittings are 8 inches in size. There are four types of sewage pumping stations. The first type is a wet well dry well combination, wherein both the wet well and the dry well are located below grade, with a dry well adjacent to the wet well. The second one is the submersible pumping station, wherein the pump is located in the wet well. The suction lift station will have a self-priming pump or a number of self-priming pumps located in the dry well. And the third one is a screw pumping station, wherein it utilizes an Archimedean screw with the motor located above grade and the screw located below grade. This is popular in the irrigation business. The submersible pumping station design has been selected for this specific project. The submersible pumps will be located in the wet well with the motor control chamber located above grade. Pumping station design would be based on system head curves traced by head calculations for particular flow values. The system head can be calculated using the equation total head equals Z plus H sub L, wherein Z is the elevation head, which is equal to 20 feet. Excuse me. And H sub L is the head loss. There are 4 methods that are used to calculate head loss due to friction. These are the Darcy-Weisbach equation, which utilizes the Moody diagram. The second one is the Hazen-Williams formula, which is an empirical equation, and this is widely used in the waterworks industry. The third one is a fanning friction factor, which makes use of the hydraulic radius. Hydraulic radius is the cross-section of the pipe divided by the wetted perimeter. And the fourth one is the use of tabulated values for head loss. ASHRAE, or American Society of Heating, Refrigeration, and Air Conditioning Engineers, has tabulated values for the friction loss of water in different pipes. And also, Canadian Standards Association has tabulated values for friction loss in the pipes containing natural gas. The head loss will be calculated using the Hazen-Williams formula. As I said earlier, the Hazen-Williams formula for head loss is an empirical equation applicable only to the flow of water in pipes larger than 2 inches and of velocities less than 10 feet per second. The reason why we would choose this type of method is, number one, sewage is made up largely of water. Second, size of the force main is 8 inches. Third, the desired maximum flow rate for this project is 900 US gallons per minute, and the velocity of such will be 2 feet per second. Using the Hazen-Williams equation for head loss, which is found in equation 11.19, page 278 of the Piping Systems Manual by B. Silwash. We have this equation for the head loss. 4.72 times the equivalent length times the flow raised to the power 1.852 all over C, which is the Hazen-Williams factor, raised to the power 1.852 times D raised to the power 4.87, okay, where D is the pipe inside the diameter in feet. And this equation is for imperial units. For standard international units, or SI, this constant 4.72 becomes 10.67. So we tabulate all the friction components in the system and determine the total equivalent length of the setup. So the unit equivalent length, like say for instance, a 45-degree elbow will be 10 feet for one elbow. It is located in table 11.12 of the Piping Systems Manual. And we total this, and the total will be the total equivalent length, which is 4,204.5 feet. The system head calculations shall be performed for each of the particular water flow rates of 300, 400, 600, 750, 900, 1050, and 1200 US gallons per minute. We will use these values to trace the system curve. The Ministry of Environment Design Guidelines for Sewage Works states that pumping station design should be based on system head calculations and curves for three conditions using the appropriate Hazen-Williams factor C. A. Low sewage level in the wet well, wherein C will be equal to 120. Median sewage level over the normal operating range in the wet well, with C equals 130. And C. Overflow sewage level in the wet well, with C equals 140. So, calculating the system head at a water flow rate of 300 US gallons per minute with a Hazen-Williams factor of C equals 120, we substitute in the equation of system head, and where Z is 20 feet, C equals 120, D equals 8 inches, and it is required to express it in feet, so 0.665. LE is equivalent length, 4,204.5 feet, and Q will be 300 US gallons per minute, and we are supposed to express it in cubic feet per second, so it's 0.668 in cubic foot per second. So the result will be a system head of 29.68 feet. So in the same manner, the system head was calculated for the rest of the flow values for 450, 600, 750, 900, 1050, and 1200. With this C equals 120, and the results were tabulated. So we find here the tabulation, the flow, and the corresponding values of system head for C equals 120. Plotting the system curve for C equals 120, we have the green colored curve here, and the ordinate is system head, and the abscissa is the flow rate in US gallons per minute. So, repeating the procedure for system head calculations for normal operating range with C equals 130, same flow values, 300, 450, 750, 900, 1050, and 1200. With C equals 130, this will be the values. And if you plot it in red, this will be the result here, the red curve. And we repeat the procedure for overflow sewage level at C equals 140, and we will tabulate the results here, same procedure, and the results will be the curve in yellow, okay, C140. And if we are going to choose a pump from the given by a manufacturer, so we plot the pump curve over the system curves here. And the normal operating point will be the intersection of the blue curve and the red curve. Okay, so at normal level, C equals 130, and the blue one, so this will be the normal operating level, okay, normal operating point. And the pump motor, however, you should make sure that the pump motor will be capable of handling the loads at these extreme points, okay, for a low sewage level and for the high overflow sewage level. And if you add, if the second pump will run, okay, together with the first pump, these are connected in parallel, so it will appear in a curve like this. Okay, so with the two pumps running, connected in parallel, so you just add, for the same head, you just add the value of the flow. So it will double the flow for a specific head value, and you will see that the operating point has now raised to a higher system head, and also the flow will increase. So at this point, it will be close to 900 US gallons per minute, and the head will be close to 80 feet, yeah, at this point. So, thank you for watching, and stay tuned for more video tutorials at Machacon Mechanical Engineering channel. Bye-bye.